Hello, my loves, and welcome to our second class of Unit 7, where today we're giving doll manufacturing conglomerate and multi-million-dollar corporation Mattel, TM, a run for its money, the way we've got these polys in our pocket. And by poly, I do, of course, mean polynomial. The question on everyone's lips, will Mr. Bolel get sued for copyright infringement for making a bad joke about a toy from the 80s? Only one way to find out. But either way, now that we know how our most basic operations work with polynomials, in other words, how we add and subtract them, let's see how to multiply them together. Now, if we think through our options, that leaves us with three cases for polynomial multiplication, the most simple of which being a monomial times a monomial. Now, hopefully the eagle-eyed among you will notice we know how to do stuff like this from Unit 6. Take a minute, pause the video, jog that memory. Let's multiply each of these together. Go ahead. Okay, so I know when in doubt, my strategy is often to chunk it out. I'm gonna show too much work. I'm gonna exercise too much caution. I'm gonna err on the side of too much rather than not enough support. So breaking it down like this, it makes it obvious, hopefully. Remembering that multiplication is commutative, I can do it in any order I want. So I know how to multiply negative 2 times 13. That's just negative 26. And I can do the same thing with my f's, g's, and h's. Well, f to the third times f to the third. When I multiply together, my exponents add. So this is f to the power of 3 plus 3. I've got g times g to the 7th multiplying together. This becomes g to the power of invisible 1 plus 7 times, I've got h to the 4th times h squared. Again, adding my exponents together, I've got h to the power of 4 plus 2. All I've got to do now is smush them together. Well, I've got negative 26 times f to the power of 3 plus 3 is f to the 6th. G to the power of 1 plus 7 gives me g to the power of 8. And h to the power of 4 plus 2 is h to the 6th. Same thing over here on the right. But now that we've got this structure in mind, we want to move to eventually being able to do these kinds of calculations in our heads. So I'm still going to chunk it. I'm just not going to write out all of my chunks. So I know how to multiply negative 6 by negative 3. That just gives me positive 18. Next up, let me look for something that pairs with a to the 4th. Well, there are no a's in my second factor, so it's just going to be a to the 4th. Same thing over here. I've got nothing to pair with the b to the 5th in the second factor, so this is just b to the 5th. I've got c to the 3rd power times c. So that's c to the power of 3 plus invisible 1, which is c to the power of 4. And d over here times d squared over here. Well, that's d to the power of invisible 1 plus 2. D to the 3rd should be our final power. Cool. Now, Unit 6 prepared us to answer questions like these. But in Unit 7, the multiplication we want to do is actually way simpler. Take each of these 4 products. Give yourself a little bit of time. Let's calculate them using what we know. Again, if you need to show a little bit too much work, be my guest, but I would encourage you to try to do these in your head. Go ahead. Okay, for our first one, I've got negative invisible 1 times 2. Negative 1 times 2 gives me negative 2. Then I've got q times q. Well, that's just q squared. For number 2, same idea. I can do negative 7 times negative 2. That gives me positive 14. I've got m times m. That's just m squared. 3 in number 3 times invisible negative 1. Well, that gives me negative 3. And then I've got y squared times y. So that's y to the power of 2 plus invisible 1, y cubed. And number 4, I've got 10 times 1/2. Half of 10 is 5. And then I've got n squared times n cubed. Again, add our powers together. 5n to the 5th should be our final answer. Nice. Now that we've seen monomials times monomials, upping the ante, let's talk about a monomial x a polynomial. Now, when I'm multiplying polynomials, it'll often look something like this. What do you think is the tool that you will likely use based on the way that this looks? If it ain't broke, don't fix it. Probably going to use what here? Go 5, 4, 3, 2, 1. Well, this setup looks a lot like a setup where I would use the distributive property. Whenever I've got, or almost always when I've got, something in parentheses with addition or subtraction and something on the outside of those parentheses, I almost always want to distribute that factor outside to each of my terms. So for the first one, right, I'm going to take x and give it to x, and I'm also going to multiply x by 1. Well, x times x in my first term is just x squared. X times 1 in my second term, well, that's just x. Again, these are not like terms. I cannot combine them. X squared plus x is my final answer. Same thing over here. I'm going to take my negative 2v and I'm going to multiply it by each of my terms individually. So for my first term, I've got negative 2v times v squared. Well, negative 2 times invisible 1 just gives me negative 2. And v times v squared would be v to the power of invisible 1 plus 2, which is 3. Same thing for negative 2 times negative 4. Well, that gives me positive 8. V times v is v squared. And last but not least, negative 2v times 3. Well, that's just negative 6v. There you go. There's your final answer. Now that you've got it, let's try it with these 3. I've got 3 examples down below. Let's use our distributive property and do some multiplication. Go ahead. All right, you're far enough ahead. Let's come back. I'm going to take, in my first example, my negative 3g, and I'm going to distribute to each of my terms. So I've got to do negative 3g times 4g and negative 3g times 1. Well, negative 3 times 4 in my first term is negative 12. G times g gives me g squared. And negative 3g times 1 in my second term, well, that's just negative 3g. Not like terms, can't put them together. There's my final answer. Same thing for number 2. I'm going to take my 7p and distribute to each of the terms inside of my parentheses. So I've got to figure out what's 7p times negative 2p to the 4th. I've got to figure out what's 7p times p cubed. And I've got to figure out what's 7p times negative 4. Well, 7 times negative 2 in my first term is negative 14. P times p to the 4th gives me p to the power of 1 plus 4, which is 5. In my second term, 7 times invisible 1 gives me positive 7. P times p to the 3rd gives me p to the power of 4. And last but not least, 7p times negative 4. Well, 7 times negative 4 is negative 28. There you go. There's your final answer. And for number 3, 4 terms, 4 distributions. So I'm going to take negative 5t squared and multiply it by t to the 3rd. I'm going to take negative 5t squared and multiply it by negative 2t squared. I'm going to take negative 5t squared and multiply it by 3t. And last but not least, I'm going to take negative 5t squared and multiply it by negative 4. In my first term, negative 5 times invisible 1 gives me negative 5. T squared times t to the 3rd, add our exponents, here's t to the 5th. Negative 5t squared times negative 2t squared. Negative 5 times negative 2 gives me plus 10. T squared times t squared, add my exponents, t to the 4th. Negative 5 times 3 in my third term is negative 15. T squared times t, add my exponents, t to the 3rd. And negative 5t squared times negative 4, well, negative 5 times negative 4 is positive 20. Attach that t squared to the end, and there's our final answer. Cool! So we've seen monomial times monomial. We've seen monomial times polynomial. If you're keeping track, that probably means our third and final case would be polynomial times polynomial. Now, as daunting as this case might appear, as we've just seen, remember that the distributive property still holds. So with this in mind, there are 3 ways that we'll think about multiplying a pair of polynomials like the quantity 2x plus 3 and the quantity x minus 4. In this video, we're just going to do the first 2, and we'll do our last one together in class. Now, knowing that the distributive property works just as normal, how do you think I could use it to simplify this product? Take a risk, take a chance, be wrong, who cares? How do you think I might be able to use the distributive property here? Alrighty, well, let me think about this 2x plus 3 on the left as a group. It's in parentheses, might as well. Well, if I take it and use the distributive property, I can give it to both the x and the negative 4 individually. So let me take my x, and I'm going to give that a 2x plus 3 by the distributive property. And then I can do the same thing with that negative 4. I can take it and I can give it a 2x plus 3 by the distributive property as well. Well, now that I'm here, notice that I can now do some distributive property again. So in my first chunk, I've got x times 2x. 2 times invisible 1 is 2. And x times x gives me x squared. Now I've got x times 3, which is just plus 3x. Now taking my negative 4, giving that to 2x, negative 4 times 2x is negative 8x, and negative 4 times 3 is negative 12. All I've got to do now, notice, is combine some like terms. This gives me 2x squared, 3x minus 8x, well, that's just negative 5x, and negative 12, I can tack on at the end. 2x squared minus 5x minus 12 is my final answer. Now you'll notice we did 2 rounds of distribution, so this method we doubly distributed. We'll call it double distribution, right? I'm just doing 2 layers of the distributive property. I'm doing it twice. Let's try it out with this example down below. I've got a plus b times c plus d. Do some double distribution here and see if you notice anything about your final product. Be creative about what you notice here. Go ahead. Alrighty. So by some double distribution, I'm going to take this whole thing a plus b, and I'm going to give it to both the c and the d individually. So I'm going to take c and multiply it by a plus b, and I'm also going to take d and multiply it by a plus b. From here, once again, I'm going to do my second round of distribution. Here's that double and double distribution. Well, c times a, by convention, we usually put it in alphabetical order, so I usually would put the a before the c. Same thing here, c times b would be plus bc, arranged alphabetically. I've got d times a, well, that would be a d, and I've got d times b, again, ordering alphabetically, plus b d. None of these are like terms. I cannot put them together, but I have asked you to observe something. If you are eagle-eyed, or maybe if you've just seen this before, what I hope you'll notice is that AC, well, isn't that just A times C? BC, isn't that just B times C? AD, isn't that just A times D? And BD, isn't that just B times D? So if you notice what I'm noticing here, after we do our double distribution, our final product has each of the terms in the first factor multiplied by each of the terms in the second factor once, which means that it is exactly the same as distributing each of our terms individually. Rather than going through all of that trouble of double distribution, I can now just take each of the things in the first factor and give it separately to each of the things in the second factor. This leads us to our second option for multiplying polynomials, a special method with a fancy name. We're going to call it METWET. Now, I like METWET for a couple reasons. Number one, it's because it sounds funny. Number two, you might have heard FOIL. Now, FOIL stands for first, outer, inner, last. The reason being, right, I can take my first two terms and multiply them together. I can take my outer two terms and multiply them together. I can take my inner two terms and multiply them together. And I can take my outer two terms, or my last two terms, sorry, and multiply them together. I personally do not like FOIL. It is a dirty four-letter F word that we cannot say. I personally like to think of what we're doing here as instead multiplying each of the terms in our first factor with each of the terms in our second factor, right? So what I'm doing is I'm taking the first term in the first factor and I'm giving it to each of the terms in the second factor. And then I'm going to take the second term in the first factor and give it to each of these terms in the second factor. With this idea in mind, try to simplify each of these products using METWET. Give yourself 30 seconds. Try it out. See how far you can. Go ahead. Let's do some METWET. METWET, 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 METWET. METWET, METWET. Okay, let's METWET. So, first up, I'm going to take 2x and multiply it by x. 2x times x gives me 2x squared. I've got 2x times negative 4, which is negative 8x. I've got 3 now being distributed to each of my other two terms. 3 times x gives me 3x, and 3 times negative 4 gives me negative 12. Combining some like terms, I've got 2x squared minus 5x minus 12. You'll notice that this is the same answer that we got above. Same thing here with 7j minus k times the quantity 3j plus 5k. I'm going to take the 7j and multiply it by the 3j. 7 times 3 gives me 21. J times j gives me j squared. I can do the same thing with 7j times 5k. This is 7 times 5 is 35. J times k, well, that's just kidding. Negative k times 3j, well, I've got negative 1 times 3, which is negative 3. And k times j, again, arranging alphabetically, should be just kidding. And finally, I've got negative k times positive 5k. Negative invisible 1 times 5 gives me negative 5. K times k is k squared. Last move, combine some like terms. So I've got 21j squared. 35 jk's minus 3 jk's would give me 32, just kidding. And finally, at the end, we'll tack on our negative 5k squared. Here is our final answer.